Okay, so the last topics in this chapter are the motions of ideal fluids. Just when we're dealing with ideal fluids, these are largely liquids. The flow of gases is quite a bit more complicated. We won't be dealing with that. And it's not all liquids. Like we'll find, you will find some liquids that in their flowing motion that they are not acting in an ideal way. So just a couple of things. First of all, these are the assumptions that we make about an ideal fluid. First of all, it's non-viscous. There's negligible friction in the flow of these fluids. So for example, molasses are very viscous. Water is non-viscous, flows very easily. And we'll only consider non-viscous fluids like water, for example. It's incompressible. That means that the density is constant. This is true for virtually all liquids, but not for gases, as we've already said. True for liquids, but not gases. Steady motion, that means that the velocity, pressure, and density of a fluid at a particular point don't change with time. So you have this steady motion. It's not changing a lot. So the velocity, pressure, and density, I'm going to abbreviate this just a little bit. The velocity, pressure, and density at a particular point do not change in time. And then finally, irrotational. That means that there's no circular motion in the fluid. There are no eddies or turbulence, for example. An eddy is like when you get water that moves around in a circular pattern before moving on. So you don't have anything like that, no rotation at all. If you're an engineer and you're moving on, you'll have whole courses that are related to all this, but the math gets quite a bit more complicated when you're dealing with non-ideal fluids. There are a couple of things that we're going to account for or look at. The first is the equation of continuity. We'll look at two different equations. The equation of continuity says that, well, let me just say it in words first. Let me erase this. The equation of continuity says that if you have a certain amount of fluid coming into a pipe, all right, then you have that same amount of fluid coming out. All right. This is based on the conservation of matter. That the same volume of fluid entering a point must leave that point. So if I have a certain volume coming in, I have to have a certain volume coming out. That's for volume. Now we can express this in this way. The area of our pipe times the velocity of the water coming in is equal to the area of the pipe coming out times the velocity of the pipe going in. Or excuse me, coming out. Let me erase this. I'm going to draw it again. So let's say, for example, that I have a pipe that looks like this. Now I have a big area over here. This is A1. And I have a certain velocity of the fluid coming into that pipe. Now, when I come over here, I have a small area, A2. So A2 has gone down. So that means that V2 is going to have to go up. So I'm going to have a faster speed so that I can get that same volume of water through that smaller opening. So let's see, its equation is based on the conservation of matter. The same volume of fluid entering a point must leave that point. If you decrease the cross-sectional area, as we did up here, then the velocity must increase. You've probably all done this. Like, for example, if you squeeze the end of a garden hose, that's all you're doing is that you're just taking your garden hose, which normally has an area like this, and then when you put your thumb over it, you just make the area a lot smaller. And so when the water comes out, it has a bigger velocity. So if you haven't done that, you can go home and try it. Now, the second equation is based on the law of conservation of energy, and it can be sort of loosely derived like this. Conservation of energy says that the energy must remain constant, and we can say that the work plus the kinetic energy plus the potential energy, then this must remain constant. And then we can say that all this divided by the volume, that is the work per unit volume, the potential energy and the kinetic energy per unit volume, that also has to remain constant. And then if I put in my expressions for work, F times D over my volume plus 1/2 mv squared over my volume plus mgh divided by volume. This has to remain constant. Cannot change based on the law of conservation of energy. And then I can get some expressions. I'm going to make some substitutions here. So the distance over my volume, that is, I have meters over cubic meters. This is going to be the same as force per unit area. And then I have here mass over volume. That's the same as density. So it's 1/2 rho v squared, where v now is my velocity. And then similarly over here, I have mass over velocity. So that just becomes rho times g times h. And this has to remain constant. That means that if I have a pipe, like I had up here, if I have a certain pressure, a certain velocity, and a certain height, my height, by the way, in this example is the same. So this would be h, and h1 would equal h2. Then I could say, let's make this F1 for A1. This is going to be V1, H1. That this is going to be equal to F2 over A2, my pressure. So let's erase that. And I'm going to replace this F2 over A2 and F1 over A1 with P1 and P2 plus 1/2 rho V2 squared plus rho g h2. Now in this case, for the example that I had up here, h1 is equal to h2. So these two terms are going to go away because they're equal. They can cancel out. All right. There's some interesting things that come up with this. By the way, I think you have a homework question where you actually have to apply this to find either the pressure or the velocity. One application is in an artery. So when I have an artery where I have this blockage, so I have a big area right here. This is my A1, and then I have a smaller area right here. From the equation of continuity, I know that the velocity here has to increase. So I have a big velocity. Now, if I write my Bernoulli's equation, I can also find out something about the pressure. I'm going to leave off that rho gh because they cancel out because my height here is the same. Now, notice here, these things have to be equal. V1 is small. V2 is big. That means that this quantity is bigger than this quantity over here. Right? That means that P2 has to decrease. So P2 is less than P1. So the pressure within this blocked artery right here is actually less than the pressure here. And that's actually a medical condition where you can actually have the artery collapse, that the pressure gets so low, the velocity through here gets so high, and the pressure through this part gets so low that the whole artery just collapses because you have such a low pressure there. Here's a clicker question. I'll let you try this on your own, but basically, I have these two standpipes. They have a certain height, h, that are all different, h, and you just want to ask, where is the pressure greatest? Is it with the small h or the big H? Where's the pressure greatest? And then what does the bottom portion of this look like? Does it look like this, where it tapers from one end to the other? Or does it look like this, where it gets bigger? So, you have this progression of pressures. What does the pipe that produces these pressures look like? Or is it just a straight pipe? It's not a straight pipe, okay? It's either tapered from left to right or right to left. I want you to tell me which it is. So you can go ahead and try that on your own and then fill it in on the online quiz. And that's the end of this chapter. You should be able to work through the homework. So hopefully you've already finished or are almost finished with the homework. And we'll move on to chapter 9, which is on thermal physics, temperature scales, and what have you.